Hello all, my name is Klaudia Dziedzic. In this presentation, I will try to explain tuning PID and PI lambda d delta controllers using the integral time absolute error criterion. This topic is related to my research. My presentation is divided into three parts. First, I will tell shortly about integer order PID and fractional order PID controllers. These controllers are very popular in industries for process control applications. Their merit consists in simplicity of design and good performance. Then, it will be a bit about particle swarm optimization. And finally, I will show design of the controller and results. So let's begin. In the last decade, fractional order dynamic systems and controllers have been studied widely in many areas of engineering. The concept of the fractional order PID controllers was proposed first 300 years ago. In fractional order calculus, the fundamental differintegration operator D, where A and T are the limits of the operation, is defined as you can see, where alpha is the order of the operation and the real part of alpha changed expression. There are two the most popular definitions used for fractional differintegral, the Riemann-Liouville definition and the Grunwald-Letnikov definition. A typical unity feedback closed-loop system is shown. The main function is to monitor the error between a measured process variable and a desired set point. From this error, a corrective signal is computed and is eventually fed back to the input side to adjust the process. For our exploration, we select two controllers. One, the basic PID, which has equation as you can see. It includes a weighted sum of three time functions which are the proportional gain, that determines the influence of the present error value on the control mechanism, the integral gain, that accounts for past values of the error, and the derivative gain, that responds for possible future values of the error based on its current rate of change. The fractional PI gamma d delta controller is described with two more parameters, which you can see. The two extra degrees give us better adjust the dynamical properties of a control system. Equations shown before are just theoretical. They are not equivalent to the cases of simulation or numerical evaluation of the fractional operators. In the case of control implementation, it is very important to obtain good approximations with a minimal set of parameters. On the other hand, when the number of parameters in the approximation increases, it increases the amount of the required memory and speed too. Because of these reasons, for directly discretizing S power R, we shall concentrate on changing S to Z domain. We choose Tastin method, which uses CFE, the continued fraction expansion, where P and Q are polynomials. The fractional PID controller can be approximated using this equation, where WZ is the discrete approximation equation of fractional order integral S power lambda or delta. Particle swarm optimization is a global optimization method based on evolutionary computational technique. It is developed from swarm intelligence inspired by social behavior of bird flocking or fish schooling. For explanation how this method works, I will suppose the following scenario. A group of birds are randomly searching for food in an area. There is only one piece of food in the area being searched. All the birds don't know where the food is, but they know how far the food is in each iteration. So what's the best strategy to find the food? The effective one is to follow the bird which is nearest to the food. In piezo, each single solution is a bird in the search space. We call it particle. All of particles have fitness values which are evaluated by the fitness function to be optimized, and have velocities which are direct the flying of the particles. The particles fly through the problem space by following the current optimum particles. Piezo is initialized with a group of random particles and then searches for optima by updating generations. In every iteration, each particle is updated by following two best values. The first one is the best solution it has achieved so far. It is called local best. And another one value that is tracked by the particle swarm optimizer is the best value, obtained so far by any particle in the population. This best value is a global best. After finding the two best values, the particle updates its velocity and positions with following equations. After finishing iteration, the best values are found. The goal is to optimize the fractional PID controller, which has 5 unknown parameters, and integral PID, which has 3. That is why we need to create a 3- and 5-dimensional solution space. To design piezo algorithm for it, we need to set parameters that will give us the best results. For both controllers, the parameters will have the same values. The most important thing to choose is fitness function. In our case, it will be integral of absolute error. Size of swarm will be 10. Algorithm will stop after 100 iterations. Our algorithm gives very hopeful results. We can see controlled closed-loop response of the system. The time responses, the minimal overshoots, as well as the variations of best fitness indicate the superiority of the fractional order controller over the integer order one. Moreover, error waveforms for plant in fractional controller is smaller than in integral controller. In conclusion, the main findings of this study are: control design goals can be achieved using numerical optimization method, particle swarm optimization. Furthermore, the results show us that fractional PID controller is much more efficient than integral one. Future plans for this research are to use other stochastic optimization algorithms and to change fitness function for maybe something more efficient. Thank you for your attention.